For the last 40 years, the security of the digital world has relied on a simple principle. Certain mathematical problems take an impossibly long time to solve with classical computers. Factorizing large integers, computing discrete logarithms, and navigating elliptic curve structures are all tasks that scale so badly that even the most determined attacker simply can't complete them within any meaningful time frame. It's what systems such as RSA, Diffie Hellman, and elliptic curve cryptography are based on. And as we know, these are all used to protect global financial institutions, government communications, industrial controls, and the everyday traffic of the internet. But with quantum computing now on the horizon, that's all about to change. Let me explain. Now, in 1994, Peter Shaw demonstrated that a sufficiently capable quantum computer could perform integer factorization and discrete logarithms in polynomial time. What this means is that once such a machine exists, the core assumptions behind today's public key cryptography no longer hold, essentially collapsing the confidentiality and authenticity guarantees we have in place today. Now, fortunately, it would seem that current quantum devices are unable to execute Shor's algorithm at the scale required to break real world keys. But the trajectory of research is clear, and to be honest, we only have to turn to the staggering development pace of AI to know just how quickly these things can evolve. There's also another point to consider. The strategic risk is not just tied to the moment quantum computers reach maturity. No, we're already observing encrypted data being intercepted and stored for later decryption when the technology catches up. That's why governments and standards bodies have acted. NIST, for example, has standardized the first generation of post quantum algorithms in Kyber, dilithium, and Sphinx Plus. And governments are issuing mandates requiring cryptographic inventories, migration plans, and hybrid deployments. But the truth is, updating global cryptography is never going to be a single event. It's a multi year engineering effort that touches every protocol, every device, and every certificate authority, to name a few. Organizations must therefore perform inventory of their cryptographic dependencies and identify where quantum vulnerable algorithms are used. Then they need to plan transitions that minimize operational risk. Look, quantum computing is not a threat because it's futuristic. It's a threat because it changes the cost of solving specific mathematical problems that modern security depends on. Once that cost changes, long-standing assumptions no longer apply. That means the responsible response is preparation, not panic, adopting to new standards, updating infrastructure, and ensuring that the foundations of digital trust remain solid as the computational landscape evolves.